is if we, for example, have 2 points, let's say point A and B, and they are connected by a beam. This beam is, well, let's say becoming shorter to this length. If I'm in point B, I see point A actually moving to the right of me, right? So in your video diagram, if this is B, point A will be here, right? So it's really relative to each other. But you see that, for example, in reality, point A will still be, well, at this location, right? So it will be, in reality, to the left of B, while it is in your video diagram to the right. And that is because it's relative to each other, right? So keep that in the back of your mind. And well, at the end, when you've got your full video diagram, you're going to look at, for example, point D, that displacement. Well, if you take it with respect to, for example, a fixed point on Earth, then you're taking it relative, well, to Earth. So then you're dealing with like the real displacement, so to say. But be aware of that difference when you're constructing these diagrams. Yeah, and for these ones, we're going to go through here. Let's see, because I'm not going to do this on the blackboard. First, you need to be aware that actually these have 2 ways of being asked. The first one is that you get like the forces and you have to calculate the, well, elongations yourself, right? So you all know that equation of the elongation, that's equal to FL over EA, right? But sometimes they also give you some note about, well, stress. That is actually the one we're going to be dealing after this. Let's see, where is it? I had the wrong one. So for example, this question, they make a note here about, well, something with stress is equal to something. I will come back to that, but it has to do with something we're changing here. But for this exercise, the first one, they don't give you that note, so always check these exercises beforehand, right? Check if they're giving you like, oh, all stress is equal, so you know that this is just a fixed constant. In this case, they don't give you anything, they just give you like the area of each beam, so the diagonals, they have an area of square root of 2, they have a certain length and so on, so you just use that in the equation for delta L. And then you can calculate these kind of, well, elongations and shortenings of your actual truss members. So if we're going to look at this exercise, they, I think, give you often a starting point on that scrap paper. You can always expect that, because otherwise you don't know where to start, and it would be a bit, well, tricky if they do that in an exam. So you can always expect like a certain starting point. And for this exercise, I'm going to try and see if this fits neatly next to each other, so you also see the exercise itself. Okay. Okay, so first the starting points. And you know certain points are fixed to the Earth in this case. So you have, for example, point A and B. You know they can move horizontally, right? But they can never move vertically. So they're somewhere existing on a horizontal line next to each other. And while the distance between those 2 points, as drawn, for example, on the top, is actually the elongation of that specific beam. So you know that there is a force in bar 5, right? Well, you're going to look at the forces they're given in almost all cases. So bar 5 is actually shortening by a half F, right? So you know that that half F can go into this F of your equation. Bar 5 is of L length, and you know that E and A are just E and A for like a horizontal or vertical member. So well, if you really calculate that for those values, you will find that it moves by a half FL over EA, and it shortens actually, right? So point B, if you're point B, you see point A moving to the right of you, right? So that's why point A is on the right of B. So be aware of that. Well, when you've done that, you're actually going to the next point. This is your starting case, actually. And for the next one, we're going to be looking at the first reference node of point G. And for that, we use beam 7. 7 is going to be shortening as well, right? So G moves down with respect to point A, so you move down on your radio diagram. How much? Yeah, well, you fill in once again that force and the same area, the same length, and so on. So you will find a half FL over EA as well, right? This I think should be 2 FL over EA. If you've got this one, you need a second reference point, right? So now we're going to be looking at bar 6. And by choosing the order, well, in these exercises, always look at what you've got already. So we had point A and B. So we can look for point G, because we can use, well, 2 bars that are connected to points we already calculated. So this 6th bar, you need to be a bit careful. First, it's intention, so that's already the different direction, so it's elongating. A different force, and also be aware that for a diagonal, of course, the length of that member is a square root of 2L. And as we saw in the exercise above, for the diagonal trusses also have a different cross-section. And if you're careful, you see that that cross-section of a square root 2A cancels the square root 2L. So in general, it will be still a 1-by-1 triangle, as you will see in a second. And that's what you see here, right? So it will go diagonally away from point B to the top left. Well, if you've got these 2 reference points, you're going to be looking at how that part of the beam moves. So if you, for example, have bar 6, the diagonal, it moves like this with respect to your angles. So you have actually perpendicular to that the displacement, right? So what you're going to do is, at those 2 locations you found, you're going to draw like these perpendicular lines, and where they intersect is actually the new point with respect to the other ones, right? So you can see that this line is diagonal perpendicular to that 6 bar, and this horizontal one is perpendicular to the 7 bar. And then they neatly intersect, and you actually found your new point G. From G, we can go to point C, actually. And point C is here on the right. So first, you do the same trick for that bar here. 9 is actually in tension, so it becomes longer. So G moves, well, to the left with respect to C, for example, or the other way around. And then you see that your new C is over here. Yeah, good question. C is indeed fixed horizontally, but those other points, they do move with respect to point C. And that's going back to the story at the beginning, but very good question. C is in reality not moving horizontally, but these points are doing something. So that's why they do have a relative displacement between each other, but this one is indeed horizontal. In our world, it's fixed. So do be aware of that indeed. So that's your first point. We can still just take it. And then we also have for C bar 4, right? So 4 is elongating, and I'm not gonna be telling you how to calculate these lengths, but each time I'm just filling in the correct force, the length, and the area of each and every of those bars, and then you find, well, the value that needs to come here. Well, if you here, once again, do those perpendicular lines for the correct bars, you find a new point C, right? And with this, you just continue, basically. So the steps are now the same for everyone. So we're going from point, we're going to look for point E. That diagonal bar is moving to the right. So it's shortening, so E is actually moving to the left of point A. And you will get these diagrams fully worked out, so don't worry if some of these steps now are a bit fast. This is bar 8, right? Moves to the left of G, so that means 8 is actually indeed elongating in tension, and you find your new point E. And then we do the same to find D with those 2 diagonals, like the one with respect to C, that's bar 3, and bar 2 over here. And when you find the intersection point of those, you actually find your new point D. And that's the one they often ask for. Well, in these exams, they also give you like these kind of diagrams, right, over here, where they ask, okay, what is correct? And often they flip a point that needs to be in tension while it's actually correct in compression, so it needs to be at the top of the bottom. So they look very much like the one you've drawn if you did it correctly, but be aware that they often just flip the direction of one of those points to get you, well, it's not misleading, but you actually need to have the correct point. Yeah, and then I don't think they asked it very often in an exam, but they can ask you the absolute like displacement like we want to know it normally, what you do then is you're going to look with respect to those points that are indeed fixed on Earth, so A, B, and C in this case. If you want to know the horizontal displacement of point D, yeah, if you take it with respect to C, which is fixed horizontally on Earth, you know the actual horizontal displacement. So that's what you can do here, for example. You're going to look at your point C, look at the horizontal displacement relative of D, and then you know the horizontal displacement of that point D. You cannot do this at C also for the vertical displacement because it's vertically not restrained, right? C can move vertically. But then you can choose A and B, of course. So then you just look with respect to A and B, the vertical displacement of D. And that's basically how you go through all of these exercises. Are these steps for the first type of, well, Willio diagram clear for everybody? Yep. Yep.
We have one question. Can you see before you start which direction it goes? Because I always start in the middle and I end up somewhere on the left side or something.
So you mean where to start with your Willio? That's a bit of insight, but don't worry, they do give you that in the exam. So they always give you a starting point, and if you go out of your paper with their given starting point, then you need to check because then probably something is going in the incorrect direction. Because indeed, yeah, if you need to make a guess, you can make the wrong guess. In an exam, it would be, well, not really a learning goal to make you guess the right spot and then have to redo it because it doesn't fit on your paper. So they give you the starting point, and if you then still go outside the scrap paper, then you're probably doing something wrong and have to check your calculations, and probably something needs to be flipped somewhere. Yeah. Okay, then, well, there was a second type of Willio diagram that's with the stress part, like that additional node. I will give you, like, let's say 15 minutes to get a start on that as well, but then we'll quickly go over that one a little bit faster. Yep. Okay, I will quickly go over that second video exercise. There is a very important distinction, and you have to look for that before you start these kind of questions. But that was this part, right? Where they state, okay, in each stress, the stress is going to be sigma, just a constant, right? Remember from the previous one, we had that they gave you the area as well, right? Of each stress, like the diagonals had the square root of 2 area. But what they basically say here is this value sigma, so sigma is F over A, right? That is your actual stress, is always constant. Any stress member, doesn't matter which one. So if you look at all these forces they've given you, it doesn't really matter because they're going to adjust the area of each part of your truss in such a way that this value is always the same for any truss in your structure, right? So you actually don't need this equation anymore, but you can rewrite this by simply substituting this part. So you get sigma L over E. This is the new equation you're going to be working with. So all those forces you don't really need. The only thing you need from these forces is whether it's plus or minus. So whether it's tension or compression. And then you simply fill in only the length of each truss member. So you just look for, okay, is my stress elongating or compressing? And what's the length of my member? Most of the cases it's either, well, just L, for example, for the horizontal and vertical ones, square root of 2L for these diagonals. But be aware, when they ask you a question with this, there is always a member that's, for example, 2L or 2L by 2L diagonally, because this L is the actual length of your member, right? So be aware of that. And besides that, it's actually completely the same as what we did in the previous step. So I'm going to ask, how confident is everybody that they can construct these diagrams themselves? Let's ask it differently. Does anybody want to see the steps of this one from A to Z? Don't think so, right? Okay, so be aware then of this difference between this part and the first one. And then I'll leave this for now. You get these elaborations as well. Here was a small thing we just discussed with some other people as well. So here they once again ask you these elongations of your members. But that question is a bit tricky because we do believe there is a mistake in here because they ask for shortening. While this beam is, if we look at GD is bar 9. And bar 9 is in tension, right? So it's not shortening. So we think this is clearly a typo in the exam and should have been elongating. And as it is a multiple choice question, one of these answers should have been correct, which is, but it's not shortening, but it's elongating. But that, I think it's B from the top of my head. But yeah, be aware that if they ask you, okay, truss 9 is shortening by this value, while it's actually elongating by that value. But that's a typo, we think. But be aware of that plus and minus value story, right? Normally plus is elongation and tension, and minus is always shortening and compression. But if you see these kind of things and you're unsure, just ask the teacher, because this is, well, probably a mistake, and this should have been elongating or whatever. But just so you know, this is also written out in the elaborations. The next exercise we were gonna treat is this one. So you can also expect these 2D structures. So the video diagrams was one of the kind of exercises you can definitely expect, because I believe it wasn't in an exam for a few years. So be aware that you can probably expect one of those. But the second type of exercises were these 2D structures, right, with all the standard beam equations. We will be doing the calculation part of this. So let's say in about 15 minutes, I saw some people already working on them. I'll start with this one as well. Okay, we'll start with the second type of exercise, the normal 2D with displacements. The first thing you were asked was like these statements, and you probably, I think you've received this one on Canvas as well. So you know maybe there are two incorrect, A and E, so the other ones are correct. So I'm not gonna highlight those, but A and E are incorrect in this case. A, first downward displacement is only due to the distributed load. And then blah, 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 blah. So actually this first part is actually already not really correct. Because what happens, as you will see in the calculation in a second, this beam, this member, causes a reaction force upwards in your beam. So if you draw the free body diagram of A to B, you also have a vertical point load at S1, which counters the distributed load. So if you only take the distributed load, you overestimate basically the downwards displacement. It's a conservative approach, but the first sentence of A is actually already incorrect because that normal force in your beam also affects that displacement. If it's a zero member, yeah, then it's only the distributed load, but you will see this in a second in the calculation as well. And then the so-called inclined beam effect need not to be used in this exercise, as the additional standard beam equations take these into account. And well, that's in general just wrong, because the standard beam equations are really the basics. And normally what you do is, for example, if you have like two hinges and let's say at B it continues on, then you calculate the rotation at B and then you put that other part besides that under an angle, and that's the inclined beam effect. We will use that at point CD at the bottom later on in this exercise. We'll also see it, well, basically in action. But that inclined beam effect, it always occurs if you have a certain rotation. And those standard beam equations, yeah, they only give you the, well, actually what's happening in this thing. So if this part, for example, was rotated, yeah, that is not taken into account by this standard beam equation. You have to do that yourself. So those two were incorrect, and all the other ones were should have been correct of this exercise. And then what they asked is first the normal force in the beam. So I'm gonna put this on the blackboard. So the normal force in that beam, you can actually calculate it by statics. So you have to draw your free body diagrams with all the internal forces. And what we're gonna do is we will be using the bottom segment of the structure, because at the top, you cannot really use it because there you will have too many unknowns. So what we do is we draw the free body diagram of the bottom part. So this is point C, probably, point C. And we have our beam with our distributed load QL. And then we've got over here something is going on, right? These are internal forces because I just made a cut at this part, so that is S2. And there will be some, well, I'm going to call it a normal force because it's in member S2 and the shear force of that member. And we know here you've got two reaction forces, right? So RC vertical and RC horizontal. And now you simply use equilibrium to find, well, your internal force. So what you can do actually is just do moment equilibrium about point C, because then these two unknowns are also cancelled, so you don't even need to bother with those. So you've got your first, the coordinate system I will be using. Your Q load is going clockwise, so you've got a negative moment, QL, times this is L squared, right? And this one is causing a counterclockwise rotation. This one goes through your point. So you've got only that actual force in S2 times L. And that should be 0, right? And from this we already know that the actual force in your member is simply QL, right? And this was already that part, so this one is 0, not necessarily 0, but you don't need it for the exercise if I'm correct. So that should have been already that first part of your exercise. That's minus QL. Why is it minus QL? We made a cut over there, right? So let's turn this off once more. We made a cut here. As you know from statics of structures, if you make a cut, the two forces on either side must be in equilibrium, right? So if I draw it, well, slightly larger over here, you had your point C, and it goes here at the top. We made a cut basically here, and this part is infinitely small, like negligible. That means that we assumed a force in this direction, NS2, but that means that in that member, it's actually in compression, right? This is that same force, but mirrored. So your S1, S2 member will be in compression. So the answer will also be, negative, as you know. So if we look at those answers they have given you, you can see that that QL should be actually a negative value, right? The top left one. That's why it's that value. Then what they ask, or they give you basically a different actual force in that member. It is still in compression, but it's 3QL. Note that this needs not to be the correct answer, blah, blah. So then we're going to calculate the downwards displacement of that point. And then we go back to this multiple response over here, why that point A was incorrect. So if we have that structure, we want to know the downwards displacement. And as you can see, A to B is actually one of your standard beams. It's just a simply supported beam. So we're going to draw now a free body diagram of that part of your structure, where you've got the hinge on one side and it goes to there. Right? We had the distributed load of Q. But then be aware that over here, we actually make a certain cut of this member, what was in compression. So you will have here at S2, this is once again equal to this force, the QL, right? So this is simply QL. And this is then S2. And now you can see already two cases arising, right? So the distributed load, as well as the vertical point load. And you combine these two to find the displacement in the middle. And actually, the next step is simply using those standard beam equations. So the first one is the distributed load. And if you have your graph with you, and this is a shame, so I'm going to draw them over here. Let's see. Over here, the bottom two. A bit higher. The Q load is simply that 5/384 QL squared. Beware for that L, in our case, that beam is 2L, right? This length. This is twice L. So be also very aware these standard beam equations are always for 1L. Look carefully at your graph whether that's also the case. Often there is some kind of 2L. So this is Q, 2L squared, and then over EI. Then you also had that QL due to that, well, S1, S2 member, and this is also why that other part of the multiple response was wrong, that actually counters that displacement is due to your distributed load. And for that you use the second one, or well, the first one actually on the screen, where F is in our case QL, that was the one we calculated, times, well, L to the power 3 is 2L to the power 3, and then divided by 48 EI, right? And I think this is already one of the answers, well, that you need there. So 5/2 QL squared, yeah. And be aware, they gave you this, right? 3QL, my bad. So 3QL, not use the calculated one, but the one they've given you in the exercise. Yeah, so this is S1. Yeah, but beware that, well, this member where if S1 moves down by a certain value, S2 as well, yeah. So these are, indeed, we calculated S1 actually, but it's the same as S2, right? So that was that question. So now we actually, so it's probably here somewhere. I think this one, right? This one, yeah. Downwards displacement of the distributed load contribution minus the contribution by the point load. Yeah. This one. To the power of, let's see that, yeah, to the power of, yeah, this should be 4. And then you got E over here as an answer. Then the displacement of S1 and thus S2 equals 0. So that beam is basically, well, that point is not moving. And now we want to calculate point E, but like if we use this bottom part as a, well, free body diagram, we don't have standard beam equations for this, right? So you need to have a little bit of reasoning here. We know this one isn't moving vertically, so we're simply gonna put this one as a roller support, right? And then you see that you have your standard beam equation once again. So what we simply do is we got our support over here, the point load over here of QL. What we do here is we say, okay, we know it's not moving vertically, so just make a roller support of that. And then you have, well, once again, your standard beam equation, or at least the start of it. Here, with this one, we can work, because we're looking for the displacement of this outer part over here at point D. And this was S2. With these kind of things, you also have to work back to the case you know, right? So we know this part. So we're going to rewrite this diagram as an actual standard beam equation by simply moving those forces over there on the right to this part. So the point load simply moves, but in reality it also has like a moment contribution over here, right? So you get QL times the length over here, which is L. So you get QL squared. And this is the first step of our diagram. And if you look at this carefully, you know that it will start well because of the bending moment moving upwards. So this part will become under an angle. And that's actually, of that first multiple response exercise, gonna be that inclined beam effect, right? Because the second step we will do in a second over here, you get basically like this. Very, very exaggerated. And this angle is the one we need to calculate here. That's this one. And for this, we can once again use the standard beam equations. So if we look at those once again, we have the standard beams for the top one there. And that one we're going to use to calculate the rotation in point C. So that's in this case point B, ml over 3 EI. So we're going to call that phi C. I think that was C, right? Yeah. Phi C, which is equal to ml over 3 EI. So m is QL squared. L is simply L for, I think in this case, right? Yep. QL squared times L, so that's that contribution, and then over 3 EI, which is simply 3 EI. That's the rotation over here. We don't need to do anything extra over there on that side, but that's the angle actually that this beam is making as well. And for this, we can use the other, like your basic standard beam equations. The first contribution is the inclined beam effect due to that one. And the second one is the actual bending of the beam itself, right? So what we calculated with that angle is simply, yeah, that left part of your beam that rotates. Yeah, and if you rotate something, it moves downwards, right? But if you start loading that part, it also bends. So this is the bending contribution, which we use as the second standard beam equation on the screen. And if you solve for that, yeah, you will find rather quickly that point B moves down, D moves down vertically. First, that alpha C, the Vc times L, plus the standard beam equation, which is, in this case, Fl to the power of 3, which is QL to the power of 3. over 3EI, right? Well, and if you plug that one in there and solve them, you will find that D moves downwards 2 over 3 QL to the power of 4 EI. Right? So that is that point D that you had to calculate. Are these steps still clear for everybody? Yeah. Does that point load here cause any rotation in that point? Yeah, it will just go straight, will be supported directly. So indeed, because we're only looking for this rotation actually, we don't bother about any movements over there. That point load will actually do nothing in any case, right? It will just be set to the ground straight away. So only the moment causes that rotation. Okay, and well, this is where this exam did stop. But as you know also from the exercises you had for your homework, is actually one more contribution that you need to consider, right? So we have the bending of point D here due to, well, what's going on at the bottom side. But in reality, that point S2 will move vertically down, as you see at the top, right? So we just, once again, fix it in place, but it's now displaced downwards, and that causes a rotation as a sort of, in Dutch, a whip-wop around point C. And you can just use the triangles and the scales of them to find how much point D moves upwards because of how much point C, S2 moves downwards, right? So S2, you calculated at the very beginning. And in this case, the displacement upwards of point D is simply 2 S2. But it could be that the ratios are a bit different, but just for your information that this could be another step to these kind of exercises, if this occurs. And with this, basically the 2D structures is what you can expect. So a little bit more complex. These kind of rotations are often part of these questions. So look carefully at what the structure is doing and how you can go in all cases, like to these kind of standard cases that you can actually, well, apply the standard beam equations. And this is also often part of the exam, like this is one of the core things you have to be able to do. Any questions about these kind of exercises? Yep. So it's a good question. Nothing, actually, because this part stays the same. So you split it actually in two. So that point C moves downwards, and that displacement of D that it causes is what you see there. But we also have the bending and so on of this beam due to QL, which is simply a different case. And because we're working with linear elastic structures, so that means we can use superposition. We just split the cases and we add them back together. So the displacement of S2 downwards causes this displacement of point D. If I add that by the displacement of point D caused by all the bending in the bottom part itself, you've got your total displacement. Is that a bit clear? I think there are some more exercises in your exercise reader that do this, right? You've got the tilting plus the bending part, and that's actually the two steps indeed. Yeah? No other questions about these exercises? Yep.
So in the one we just did here, there was also a force QL at the end, but also a moment to find the displacement.
Let's see, so this one.
Yeah.
This one, right?
So yeah, on part like on part D at the end of the beam, was there a moment or not?
No. So at this point, there's only a point load. But if you're looking in point C, that force is a distance away from you, right? And then we are working with the definition of a bending moment. So if I'm only considering this part, these two forces are basically representing anything that's going on that side of that point. So what's going on C to D. So both the vertical load plus, well, that distance times your force. But this is simply that second part. So exactly, and there is no moment. Yeah. Okay. no other questions, then we'll continue. The next exercise was, I believe, a cross-sectional one. They do give them occasionally. I won't be doing like all the steps, so the neutral axis, I for now believe that most people are able to do that. But we'll zoom a bit into the parts of the stresses, like the bending stresses and the shear stresses. So that will be the focus of that one.
Probably get the best rhythm in the world ever animals. That's true. City is true. So to your family? You actually went out?
I would, but I didn't.
So they give you 8 for this one if you have it. How we're going to use that space. You're going to get two cases right there. Not in the whole face.
It's so crazy when I literally didn't even submit number 3. Like submission 3.
I don't think, like, it depends on the teacher probably, but I don't think you need to.
Yeah, I think it's like just in case of they have like a digital evidence or something. It's crazy. I got for workshop models and sketches a good. Every time we have that workshop modelation, I'm like, I have nothing. And they would just laugh at me.
It's chill, they seem chill.
So chill. Stop scaring me. Yeah, she's Because like, I don't know. Huh? I found my box and I recycled the old one. I told you. Do you need a box?
Yeah, but I have one next time, so it's good. Go for it. As long as you get it online, go for it, make it better.
No, but like I don't know if it's because of like money saving shit. Because my mom even told me like there's not enough money for the house. But like at least for me, I don't know.
Probably move though.
I want to. We're gonna start looking into something.
It's a nice place.
Yeah. But I also don't think it would. Yeah, no, I would have to be forced to go cheaper. Because I don't think cars at the maximum
thought that was like an exception.
You should call Valve back on that, by the way. I should get you, honest. I'm really concerned. Is she still in there? Like the girl that I was with yesterday? Yeah, it's wrong. The girl that I was with yesterday, I texted. I was like, "How was it?" Like, is she? Huh? I suppose she doesn't respond.
Who?
I'm gonna pee.
Oh, okay.
I drank like a big bottle.
No, so small. I think it's Tuesday because you are Do you know how the exam is like? How many questions of applying mechanics we get? Like two? I don't know. Because an old exam, no? You get 100. Yeah, but I think the old exam is just I think the old exam just has materials. There's a materials one. There's also the applied mechanics. So that's question, three questions. Oh, that's the one we're doing now. Yeah. This one, they took this one from the old place. And this one, this is, and this one. Oh, this one too. So they just took on the phone. And they added one more too.
I think deze, ja, het zit zien wel. Okay, so some small notes on the cross-sectional properties. I won't do like the neutral axis. I hope you understand that at this point. I am going to start with this part. They ask you basically a segment of the contribution to your total second moment of area, right? So normally you do that for all the separate rectangles or triangles in your structure and you combine them. Here, be careful that they ask you for only the top flange. So that's this part over here. Yeah, and how you had to do this was, just as a reminder, you've got the contribution of the shape itself. So that's for rectangles, for example, 1/12 bh to the power 3. But also don't forget the contribution by the distance, right? So the distance to your neutral axis, to the center of the of your shape, basically. So in this case, it was 2.5a with the 3a line of gravity. And then the next step was calculate this for the entire cross-section. You do this, but for all the shapes in your cross-section. I hope that is clear for everybody. Other people who still have questions about the neutral axis in itself and this part? Good, that's good to hear. Then we just skip straight to the questions about the stresses, actually. So the first one they're going to ask you here is the bending stresses. And some notes about that is bending stresses you could calculate with mz over I, right? That z is the distance to the outermost fibers of your cross-section. So if we, for example, have a rectangle, neutral axis is in the middle, this is simply z. Well, or this one. But be aware that in case of these kind of shapes, where the neutral axis is not necessarily in the center, that set has two components, right? The bottom side of our cross-section and the top side. They are both different. One is in tension, one is in compression. And you both have to calculate them with, well, mz over I. I is just calculated as the second moment of area. And m and z are the ones you need to consider here. Well, m was given for this structure. It was the 1/4 FL. You can also do this with statics if they ask you to find that one. But be very, very careful here with what kind of bending moment you're dealing with. Normally, if you just bend the beam downwards, everybody knows top is in compression, bottom is in tension. But at this support, you get a so-called hogging bending moment. And a hogging bending moment is actually in the opposite direction. So that means that your top side is in tension and the bottom side is in compression. So if they ask you these questions, don't blindly fill in, okay, the top is in compression, the bottom is in tension. No, look at the structural scheme and look at whether you have positive or negative bending moments. So either sagging, which is the normal bending moment, or hogging, where you're pushing, well, the structure upwards. What does that mean for this question? Well, we're looking at that maximum point. So if you're pushing this cross-section upwards, the top will be the side where the tension will be, and the bottom side will be the one that has the compression. And then you just fill in this equation, right? So the bending moment was already given, tension at the top, so the Z is 3.5a, and this one is given as well. And then you find your tensile stresses at the top. And then at the bottom was your compression, but there, of course, it's 2.5a. So that is some notes on your bending moment diagram. These are different values. That's also perfectly fine. Tension and compression are also, well, stresses of a different nature. So be aware of these differences, and that you also have to, well, look at both sides if your cross-section is not symmetric vertically.
And could you just repeat again how we know if it's
this part?
Yeah, this part.
Yeah. So normally if we have like a beam, we bend it, right? And they always give the example where the top fibers are compressed, the bottom is pulled. But that part where B is, it's basically flipped. So you're pushing the structure, yeah, not sure if this works, but upwards. So that means that the fibers at the top start to be in tension, whereas the bottom ones will be in compression. Whereas for this case, it's the opposite way. It's basically mirrored. And yes, you do have to know a bit about how these diagrams look. But yeah, the basic cases, I hope you can already recognize a little bit. But often if you have a continuous beam with a support that's, well, hinged to it, so you don't interrupt the beam, like it's not two parts, but like it's beneath it, you often have like this force that is pushing it upwards. And that's the cases where you often get like these hogging bending moments to the opposite direction. Does that make a bit sense?
Yeah.
And you can always like get these diagrams, right? So this is basic statics. Yeah, exactly. So if you're not sure intuitively about whether it's hogging or sagging bending moment, just calculate it for yourself. Yeah. Okay, that's bending. Then for shear stresses, it works, of course, a bit differently. You have the equation Vs over Bi for that. I is, once again, the second moment of area. V is just the maximum shear in your structure. And then you only have S and B that you basically need to consider. Some notes on the shear stresses. They are always maximum at your neutral axis. So if they ask for maximum shear stress, do the one at the neutral axis. And then the further you move away from that neutral axis, the lower your shear stresses become. So at the outer fiber, shear is actually 0, in contrast to the bending moments, right? The bending stresses. And that's also, if we look at the exam question, how they formulated this question is, well, you probably need to calculate all of them, but you can already say, okay, tau 2 was the one at the neutral axis. Yeah, that's the maximum shear stress, period. So we know C is already correct. That means that also E must be correct. So this way you can already intuitively cancel out or cross some answers. Yeah, tau 3 is smaller than tau 1. I would say just calculate them. You can see it if you have written down your equations. You're like, oh yeah, I could have seen why one is smaller than the other, but you can just calculate them. And how you do that for shear is, for example, if we look at the bottom section, so this was tau 1, that's basically where those two legs start. The S is the first moment of area of one of the sides of your cross section. So I've, in red, chosen to look at the bottom side of my, well, where I'm looking at the shear stress. Why? Because that's the fewest contributions to your shear stress. Because for the top one, I had to look at, okay, 2 vertical, 1 horizontal. So just choose the side with the fewest amount of members to your cross section. And then it's simply the first moment of area, so not the second one. And what we do is the area of that block, so 6.25a wide, 1a high, and 2a is then the distance from the center of that geometry to your neutral axis, so the overall neutral axis of your structure. And this is twice because left and right, simply the same. For B, you always choose, well, the area where this section basically continues. So we've got 2 segments where it's touching, well, of A wide, so B is going to be 2A in this case. The shear stress is transferred here, and that's your B. So not this part, not the entirety, not only one, no, this plus this is going to be where the shear is transferred. So B is 2A. And if you plug that in, you get these kind of values. So you find 0.15 F over A squared for shear stress at the bottom side. Then you have tau 2, that was the largest one. You do the same again, so we still have the contributions of the 2 bottom legs, but you also have like this 1.5a height and a wide segment on the left and the right, which has a distance of a to the neutral axis. So that's this contribution over here. 28a to the power 3, well, the 2a is still the same, right? So 2 of those legs. And now this is also a check for yourself. This value should be higher than this one, which was the case, right? So always check yourself with these kind of things. And then you can do the same for that one. I'm not going to repeat the story, but I think this should be clear. And you can see that this is 0.12, so tau 3 is lower than tau 1. Is this clear how you calculate shear stresses also with the first moment of area, or is there still some confusion somewhere? Nothing? That's good. Then that's basically what you can expect of these cross-sectional properties. So the only ones that are normally more of a challenge are the ones where you calculate shear and the bending stresses. But if you take into account these notes, so for bending stresses, carefully choose compression or tension at the bottom or the top. Be aware that the distribution of your bending stresses can look like this, so that it's not the same on both sides. And then for shear, just be aware of where it's maximum and how you can calculate it with like the first moment of area, for example. And that's basically everything you need to know for cross-sectional properties. Then we have bit of time left. Let's say in about 5 or 10 minutes, some last notes on the last type of question you can expect, which is the 3D one. So we're going maybe a bit over time, but I'm trying to keep it not too much. Top. No. Well. Okay, some last notes on 3D structures. These 3D structures you can expect, but not in the most complex forms, right? You've maybe seen in the old exams, they're often limited to these kind of clamps and then some kind of extensions of that. So not like with all the rollers and all the things coming together. So they're often not too complicated. But how these questions often start is, well, first you need to, just like with 2D, go back to the standard beam equations you know, right? So for this one, we simply know, okay, we have to go back to this clamped configuration. If we then look at what you can do here is, okay, we've got two forces. Those simply, just like as you do it in 2D, translate to that point. So we've got F, and just the vertical F load I neglected here for the reason that, well, actual deformations are so small we take them into account. So yes, there is a force F pushing into that vertical member, but because it doesn't contribute to the deformations, I just leave it out. Could have drawn here, but leaving it out. And then you've got two moment contributions, right? So if we look here, just always use the right-hand rule. We've got due to that F load at C, that FL, and then same for this one, we get torsion about point B. That's the FL over there. And using this, we are basically at our starting point. Well, what you're going to do now is simply do basically the same as what you did for the 2D ones, but you have to be very careful in these cases because, yeah, it's not 2D anymore, not one plane, but we're looking at two planes. So there are some ways to do this. I often prefer to write them down as those separate planes. So for example, XZ plane is basically looking from the left to the structure. And if we then looked at our structure here, you can see, okay, the only contribution in that plane is that F load. The torsion is not included in these diagrams, right? Because it's simply rotating of that beam. So that's not yet over here. Then we've got AB, which is YZ. So that's looking from the front of your structure. And then you can also see from this, right, that's simply that F load pointing downwards. But you can also look at from here. It's simply that FL rotating about your structure. So now you've got basically the rotations in the two directions. Are these steps clear? Often these 3D are indeed a bit, you need to be very careful because it's a lot of angles and you need to be a bit wary of all the directions. Yes? Oh no, that's the thing. But be careful with these and do it in a way that it's systematically for yourself so that you really have your separate cases. And then, yeah, what the next step is basically just doing the thing we did for 2D structures. But then it's in 3D, so we get some results that is occurring in 3D. It's moving a bit in this direction and as well in that direction, for example. There is here also, you will get this, but the calculations are here. And these are just the standard beam equations for cantilevers with a moment at the end, for example, or a force. And there is something written in the applied mechanics reader about the directions as well. So often this is always the shortest from one to the other axis. But if you want to refresh this, you can look into page 177 of your applied mechanics reader. Yeah, and then you're going to continue throughout the structure, right? So then you know the rotation at point B. So now we do basically the inclined beam effect over here at point B. So this thing is rotated in space. And then you can also find bending due to those forces in itself. And you can see here that, once again, those inclined beam effects. And you need to be very careful, once again, with which rotation belongs to which direction. But in essence, this is exactly the same as what we did. So this is actually how it looks, right, with the vertical force as well. But in essence, this is the same as 2D. But the only thing you have to be doing is like splitting it in those two planes. And don't forget any forces. So double check always if you excluded all the correct forces and if you split it into the two planes, if everything is at the correct location. So these are some small notes on 3D structures. You can find this elaboration. We will send it, I believe, just after you left. So then you can look at this carefully and see, which belongs where. Any questions regarding this part, or any, well, more general questions you have about the course at this point? No yet? Then we will be, I think there are still a few questions left, so we will be staying a while. But then I wish you a lot of success on your exam Wednesday, and hopefully you all manage to get a good grade.
My mom was like, didn't you already have purple phone whenever before? I was like, yeah, nice was.
Yeah, then we're talking about the same thing. So this is also 3D, right? So let's go back. This was the first. So this is the vertical member.
Do you want to carry this?
And then in this one, why is there enough weight force here?
Yeah. So this is looking at the top from 3D. So as you see here, y x. So this I'm looking at the top of the structure. So this force is that one over there.
Oh right, okay,
Yeah.
YX.
Yeah, exactly. Yeah, it shows here
Yeah.
the two. So yeah, there are more directions. You can like also look from the front, but as you see, there is nothing going on in that vertical load.
Yeah.
So that's why I indeed chose to
Yeah.
split it in those two cases, and then I believe here you also see that it includes how much this thing rotated, because B did rotate because of the trickiest part of this entire 3D question is always what belongs where.
Yeah.
What is rotating exactly. Just do that very carefully and double check.
And in these, like, you should never try to find like